Hi, my name is Sean Doyle, and I'm back with the fourth episode in my multi-part video series entitled Introduction to Programming for FRC Robots. In this video, I'm going to be talking about subsystems. So the first thing I want to talk about is what is a subsystem. So a class provided by WPILib is called subsystem base, and this is the class that all of our subsystems derive from. The main purpose of this class in WPILib is to prevent commands from trying to access and actuate the same motors or any types of actuators at the same time. So once again, we haven't talked about commands yet. This will come up in a later video. But for now, you can just think of commands as just actions that the robot can do. And so subsystems ensure that different commands don't try and actuate the same actuators at the same time. So remember, we talked about actuators in the last video. They're anything that cause motion on the robot. So a subsystem is usually just like a collection of actuators. Here we have a drivetrain, which has a bunch of motors in it that work together in order to move the drive base around. So you wouldn't want two different commands trying to tell the robot to do two different things with the drivetrain at the same time. Like, for example, if you had a command to drive the robot forward, you wouldn't want that one to be running at the same time as a command that turns the robot is running, because then the drivetrain would be confused. So subsystems are classes where you group together actuators at a bare minimum, and then commands require specific subsystems, and that prevents commands that require the same subsystems from using the same motors at the same time. So that was a little bit confusing because we haven't talked about commands yet, but just to put it simply, you can just think of subsystems as a collection of actuators working together to accomplish a purpose, like this drivetrain here with all these motors here. And to further the definition, sometimes sensors can be used within subsystems as well. So for example, I have a picture of a Navex gyroscope here, which we use within our subsystem, within our drivetrain subsystem, because it is useful to know the angle of the robot when moving it around. So why don't I continue with the drivetrain example and show some code as to what our drivetrain subsystem looks like. So in this first line here, we have a class drivetrain which extends subsystem base. So subsystem base is the class I talked about in the previous slide as belonging to WPILib. And like I said, all of our subsystems extend from this subsystem base because subsystem base is the interface that WPILib provides that allows commands to easily state what subsystems they require. So now we can move on to the next couple lines here where we have a method called move using gyro for the drivetrain, which takes a forward backward speed, a rotation amount, some flags, and then a heading direction for it to move towards. So as you can see here, move using gyro is a very intuitive method name. You want to move the robot, you give it a forward backward speed, you give it a rotation speed, and then the drivetrain subsystem, which owns the actuators that make up the drivetrain subsystem, will then go and do whatever speed and rotation that is commanded. So basically, the methods within a subsystem should allow for a useful and intuitive interface for using a bunch of actuators together. In this case, the drivetrain has actuators moving the wheels on the robot. So move using gyro is an intuitive and understandable way of commanding those actuators using this subsystem. The reason why this is move using gyro instead of move is because we like to use our gyroscope while moving to make sure that we stay on a straight line and that our wheels and that one side of our drivetrain doesn't overpower the other side and we start drifting off to one side or another, which is why this is move using gyro as opposed to move. So it's important to descriptively name methods within subsystems, especially so that any users know exactly what they're doing when they call a method on a subsystem. I have another example of a method down here, public void stop. This is very simple. It's just a method within drivetrain to stop the drivetrain. And once again, it's clearly named. It's providing a useful function for all the actuators on the drivetrain working together, which is why it's part of the drivetrain subsystem. So basically, the big takeaway here is that methods within subsystems should provide useful and descriptive interfaces for other classes and other users to use the actuators and sensors that make up whatever subsystem is being written. Like I said, with drivetrain as a subsystem, move using gyro is a descriptive and useful name for commanding all the motors that move the robot and turn the robot, which is why this method is in drivetrain. And the same thing for stop, where stop is a useful method and descriptively named that clearly allows any user to stop the drivetrain whenever they need to within any other class or command. So the next thing I want to talk about are default commands. So once again, we haven't talked about commands yet. That'll be in an up-and-coming video. But there are these special commands called default commands, which are run at any time when no other command is requiring a subsystem. So once again, talking about the drivetrain, we have a default command called teleop command, which is the command that runs, which takes input from the teleop controllers and then commands the drivetrain to move with those inputs that it receives. So basically, we want this command running at any time when no other command is running that requires the drivetrain. If we have like an automatic line up to goal button that the user presses, that button will trigger a command that also requires the drivetrain and will interrupt this teleop command, and it'll run that command. Once that command finishes, then teleop command will come back on. And this sort of idea is what allows us to use joysticks to run the robot around, and then we can press a button to go off and do something with the robot autonomously, and then right after that command is finished running, it goes right back to teleop joystick control. So I have like an example of the scheduler here, which I talked about in the very first video, where remember scheduler is just the loop that runs over and over again while the robot's going around, and the commands that are on the scheduler are what are actually run while the robot is moving. So in this example, teleop command is currently on the scheduler because right now no other commands require the drivetrain, so teleop command is running. But if I put drive forward onto the scheduler, then teleop command will get kicked off and drive forward will be what's run at that time. Both drive forward and teleop command require the drivetrain subsystem, but when a command gets put on the scheduler, the default command gets taken off. So drive forward will run for a while, and then once that's finished, teleop command will come right back onto the scheduler because that's the default command. So the important thing to remember here is that there are these special things called default commands, which the subsystems set, and these are basically the commands that are running when no other command requires that same subsystem. So the last thing I want to talk about with subsystems are mock versus real subsystems. So if you remember from the previous video where I talked about sensors, I said that there was a way for us to, in software, tell the robot that it doesn't have a sensor and then create a mock version of that sensor so that the same code can be run on different robots with different hardware capabilities. The same thing can go with subsystems. So for example, if one robot has a shooter on it and another robot does not, then we would have a shooter subsystem from which two classes derive from it, a real shooter and then a mock shooter. And in our configuration file, we would specify for each particular robot that one robot has a real shooter and it would construct a real shooter with all the necessary actuators and whatever that the shooter has. And on the other robot, we would say it does not have a shooter, so it would create a mock shooter which wouldn't need to construct any actuators. And this allows us to be very modular with our code and allows us to run the same code on different robots with different capabilities and easily and dynamically change those capabilities in our code. So basically this is the analog of what we had for sensors in the last video. Like I said in the last video, we don't right now have the capability to mock out actuators simply because we didn't think it was necessary with the ability to mock out actual subsystems. So basically either a robot has a subsystem or it doesn't, and we're able to construct a real version of that subsystem in the code or a mock one. Why don't we jump into an example now? So here I pulled up VS Code with our latest code from this past year, 2020. The first thing I want to draw your attention to is the folder division here. So we have a whole folder entitled Subsystems, which is where all of our subsystems are stored. And now for each subsystem, it's a folder in and of itself, which if we look at the intake, for example, is usually made up of about 3 classes. There's the intake base class, the mock intake, and the real intake. So like I said, we have mock and real subsystems, and because there are mock and real subsystems, that means that we need a base class from which those classes derive from. So if we take a look at the intake base class, this is an abstract class, which I think I went over in a previous video. It just means that any class that derives from intake base, any class that is a child of intake base, is required to override and implement any methods that are abstract within this base class. So all of these methods are abstract: run intake, stop intake, deploy intake, and retract intake. So any classes that derive from intake base need to fill in the details for all of these methods. So why don't we take a look at one of those such classes. So here's mock intake, which extends intake base, intake base, like it was the last class we looked at, which is that abstract class. If you look here, all of those methods are filled in: run intake, stop intake, deploy intake, and retract intake. Now, basically, there's a whole lot of nothing going on here because mock intake is a mock intake. We use this class when we don't actually have a real intake on the robot. So stop intake just does a printout and sets a variable to 0. Deploy and retract intake look like they just print things out. Nothing's being done here. No actuators are being moved. Then if we took a look at real intake, on the other hand, here's where there is a lot of actual programming. So once again, we have real intake, which extends intake base. And so it also overrides and implements all of those methods that intake base had. So once again, we have run intake, stop intake, deploy intake, and retract intake. And in here, in the constructor for real intake, we can see a couple of new things. We have an intake controller. So here's an actuator here. Looks like this intake had a Talon SRX controller, and it also looks like it had a double solenoid. So we have these two actuators which are created in the constructor for real intake, and then they're used within the methods to real intake. So in run intake, looks like it takes a speed as a parameter and it sets that intake controller to the speed, and then stop intake just stops the motor. Then deploy intake also quite predictably takes the deployment solenoid and extends the piston, and then retract intake retracts the piston. So this is a pretty simple subsystem, probably the simplest subsystem we had. The subsystem didn't have any sensors within it, so a lot of these methods are pretty simple, as you can see. But if we were to take a look at the drivetrain, for example, and the real drivetrain, and here is move using gyro, methods can get pretty complex and pretty long. All of this right here is all move using gyro. It even goes all the way down here. And that's because this method needs a lot of logic in order to figure out what direction the drivetrain is trying to move and whether it's trying to turn and how much correction should be happening. So this video has been an overview of how we do our subsystems on Team 4905. We have often changed this up from year to year. Sometimes we don't include sensors at all in our subsystems. Sometimes we allow for some sensors but not others. So subsystems are an ongoing debate within our team for how exactly they should be organized and what should be included in subsystems and what should be not included. But this year, this is the approach that we took, where actuators and some sensors are within subsystems, and subsystems provide a useful interface for other classes such as commands to run actuators together. Thanks for watching.